So today we're starting our journey of actually building a computer. You've probably all heard that computers internally only have zeros and ones. And the reason that they only have zeros and ones is because that's what they can get away with. It's simplest to have only two possible values that you need to maintain, and that's going to be enough, as we will see today. We're starting with the completely theoretical, logical kind of analysis of how to deal with zeros and ones. And later in Unit 3, we'll actually talk about how these abstract 0 and 1 signals directly are implemented as chips inside a computer. So let's talk about the abstract 0 and 1, on and off, true or false, not, no and yes, 0 and 1. In general, we can use all these names to refer to each one of two different physical values that are maintained somewhere in the system. We will use 0 and 1 for the rest of this unit, but that's completely general. So what can we do if we only have zeros and ones? Well, we can do some kind of basic operations on them. For example, the AND operation takes two 0, 1 signals and returns 1 only if both of them were 1. So if you have 0 and 1, the result is 0. But if you have 1 and 1, the result is 1. We can actually see all the different possibilities for combining two values of zeros and ones into the result, which is the AND of them, in a little table that is called the truth table, because it actually gives all the different possibilities of the inputs of x and of y, and for each one of these possibilities, it lists what is the output, what is x and y. So AND is one of the possible operations. Here's another very popular one, or it returns 1 if any one of the two inputs is true, is 1, or even if both of them are 1. The only time that it returns a 0 is if both x and y are 0. And here's a third interesting operation. This one is a unary operation. It only takes a single input bit as input, x, and returns the opposite of it. So return for if the input is 0, the output is 1. If the input is 1, the output is 0. So these are possible, very simple operations on Boolean numbers, sort of like addition and multiplication and maybe other kind of operations are operations on integers or on real numbers. These are operations on Boolean numbers. Once we have operations, we can start combining them just like we combine arithmetic operations in arithmetic formulas. So for example, let us try to evaluate what would be the expression of not 0 or 1 and 1. Notice that we have parentheses to give us the priority here. So the way we evaluate is very simple. We know how to evaluate 1 and 1, which is 1. So the whole thing simplifies to not 0 and 1, or 1. We know how to evaluate 0 or 1. That's going to be 1 because it's an OR operation. So that's equal to not 1. And now we know how to evaluate not 1. That's simply 0. All very simple, and we can do that. Now, once we know how to evaluate Boolean expressions over values, over 0, 1 values, then we can actually get general expressions, general functions that takes indeterminates x, y, z as inputs, and for each value of x, y, z, produce an output. So for example, I can define a function of three inputs, x, y, and z, that basically tends x and y, or not x and z. And look in the parentheses to see the priorities that I was thinking about. Of course, I could define any other function by any other Boolean formula, and that would give me a function. If we want to know what kind of function is that, well, we can actually list all the possible values of x, y, and z, and for each one of them, try to write down what is the value of the function. The really nice thing about Boolean values is the fact that there are only a finite number of possible inputs, and we can actually list each one of them. This is completely different from functions that you've learned in third grade, where you have functions from integers to integers, and there are infinitely many integers, so you can never write down the function in a complete specification of all the possible values. But here we can actually write down all the possible values that the triplet x, y, z can have. We can have x0, y0, and z0 that corresponds to the first row in the table, and so on, until the last row of the table that corresponds to all three of them being 1. Now for each one of these rows, we can just evaluate the function, what is the function f of x, y, z defined by the previous formula for these values. For example, let's look at the second row. In the second row, we have x equals 0, y equals 0, z equals 1. And we can just plug in the numbers 0, 0, 1 into the formula. Every time we have an x, we put a 0 there. Every time we have a y, we put a 0 there. Every time we have a z, we put a 1 there. And now we just get a formula with constants in it. And we can evaluate it just like we did in the previous slide. And we can figure out that that is 1, that the second row should get a value of 1. We can do this similarly for each one of the possible rows. And we can completely fill the table. And now notice that this table of values completely gives you the same information as the previous expression did. It completely specifies the function, the Boolean function that we just had. The first way we described the function was as a formula. The second way we described the function was as a truth table. And these are two completely identical definitions, ways to describe the same Boolean function. So now, once we know we can describe Boolean functions using formulas, and basically we have general Boolean expressions, we can actually try to find what are a bunch of Boolean identities that always give us equality. For example, we can always see that x and y, whatever the values of x and y is exactly equal to y and x. This is called the commutative law. We have a similar phenomena for x or y equals y or x. So these are like commutative laws that hold for these Boolean algebra, in this Boolean algebra. There are a bunch of other kind of identities. For example, the well-known associative law. If you have x and y and z, it's the same thing if you first do x and y, or whether you first do y and z. Similar thing happens for or. Another well-known law is a distributive law. If you have x and y or z, that turns out to be exactly equal to x and y, all that, or x and z. Now, as opposed to the usual arithmetic, where we only have a distributed law of multiplication over addition, here we have both the distributive law of and over or, and the dual law of distributive law of or over and. The same trick works if you want to do x or y and z, that's x or y, and x or z. Now there are also laws called De Morgan laws that govern how knots work, how they interrelate with and or. These laws are called De Morgan laws, and they say the following interesting thing. If you take x and y and do a knot on all of that, that's equivalent to first doing knot of x and oring that to knot of y. And we have the dual one, that if you have knot of x or y, that's exactly equal to knot of x and knot of y. Now, all these laws can be easily proved, if you wish, not if you wish, really proved by simply listing all the possibilities in a truth table and verifying that they get the same truth table for the left-hand side and the right-hand side. Now, there are a bunch of other laws, and we can use them to actually do manipulations on Boolean algebra. So, for example, once we have a formula, for example, the formula that you see here, not of not x and not x or y, for example, it could be any other formula, we can now start applying some of these identities to change its form, to simplify it, or to just to bring it into a different format. So, for example, the first thing we can do here is look at the second part, at the last sub-expression, the not x or y. We can use De Morgan law here and basically convert it to not x and not y. Now, if you look what we have here, we can use the associative law. Because we have not x and not y, we can change the order of doing the and. And we get another expression which is identical using the associative law. At this point, we have something really interesting at the beginning. We have not x and not x. That can be just simplified to not x. Why is that? Because we can actually see also, that's another identity that we didn't explicitly list, but it's easy to verify in the same way, that if you take any value w, in our case w is not x, and do w and w, that's completely equivalent to w. Now, this is called the idempotence law, and we can thus simplify the previous expression by simply removing one of these w's, one of these not x's. Now we're ready to use De Morgan law again, and now we got into not x or not y. Now again, here's another law that we didn't list explicitly, but you obviously all know that not x is always equal to x. So using double negation law, we can simplify that to x or y. So that just gives you some kind of demonstration that you can basically just manipulate Boolean expressions, sort of like you manipulate arithmetic expressions in elementary school. There's another way to get the same conclusion, the same equivalence, without actually going through these algebraic manipulations, simply by actually looking at the truth table. We take the expression, we build the truth table for it, and we've already seen how to take an expression and find its truth table, and then we get the truth table that you see on the board. Now, once you have this truth table, you can say, I know this truth table. This is exactly the truth table of the OR function. And then that immediately proves that the expression on the top is completely equivalent to x or y, as we've derived using algebraic methods previously. Now, of course, it's not completely, you won't always be so lucky to do some kind of big truth table and recognize what it is and immediately see a better and nicer and simpler expression that gives you the same table. Sometimes you will have to do algebraic manipulations, but on the other hand, it's not always true that algebraic manipulations are easy to do in the sense of finding a very simple expression. So, but in general, in principle, you can use both of these methods to actually simplify Boolean expressions or find alternative forms that give you the same Boolean expressions. So we've just finished our first unit describing how to manipulate logical values. Notice that we're still keeping our abstract point of view of just logical values and not thinking about any physical realization that we will have inside our computer. In the third unit, we'll actually switch our point of view and start talking about these same kind of phenomena, but from the point of view of real chips and real gates that we have inside a computer. But before we get to that, in the next unit, we'll keep maintaining our theoretical point of view and start talking about the following problem. How can we construct a function from basic operations? How does that, this is exactly the kind of things we will need to do when constructing hardware. We know what it wants to do, but we'll have to actually construct it from Boolean operations, and we'll try to see how that is done, first from a theoretical point of view in the next unit.